Hi, let's see this lead code question. Find k closest element 658th one. So this is not a traditional sliding window approach question, but it is a combination of binary search and sliding window. So let's see what what binary search is first, and then let's see how we can solve it with the combination of binary and sliding window. So to understand binary search, I came up with an example of Mario. So binary search technique is generally used because it reduces search time of an element inside an array by half. So for example, if you're looking for an element 8 in in this element in this array, so you have to search through all the numbers in this array, right? So you have to first go to the element 1 and then 2 and then 3 and then 4, and you basically traverse through the entire array to find A, and then your complexity would be n. So binary search will drastically reduce your search time. To understand this deeper, we'll see an example of Mario. I'm sure many of you know what Mario is. Mario is the guy who goes and collects coins in random fields. So even as a kid, I used to play a lot of Mario. So let's try to understand this with Mario. Um, so you know that Mario collects gold coins, right? So let's say this is his field, and then he has gold here, and then let's say he has diamonds here. So if this field is divided into half, and then he has gold coins here, and then if he has like diamonds here, right? So this time let's say Mario's goal is to collect diamonds and not gold. So if Mario can, this is his entry point, let's say. So if this Mario guy wants to collect diamonds and not gold this time, what he has to do is go, if this search area is like maybe 100 kilometers. So this, let's say this spans over 100 kilometers, and then this also spans through 100 kilometers. So if this guy is traveling, if this guy wants diamonds, and then if he has to travel through the entire field, then it is very difficult for him, and it is an unnecessary hassle for him to travel that extra distance of 100 kilometers. If he can just directly jump to a point where he can just only find diamonds, right? So if someone tells him that this is the point, okay, this after this 100-kilometer point is where you can find diamonds. So he would just teleport from there to here, and he will not have to search this 100 kilometers radius where he's only finding gold. So this is basically the concept of binary search. And let's try to understand with this with another real example. Mm. Yeah, so I'm taking an array here, and then let's say we have to find an element X. So let's say this is a target element, and then we are searching for this element through by using binary search. So how do you do binary searches? You basically take your initial you start your window with left equal to 0, and then right equal to uh, length minus 1, which is 7 in this case. So length is 8, right? So 8 minus 1 is 7. So you start your window by taking start by keeping the starting index at 0, and then the last end index would be the end of the array. And then you basically find a midpoint using left and right by doing this. Left plus right plus by 2. So 0 plus 7 by 2 would be 3. So let's see, 0, 1, 2, 3, 4, 5, 6, 7. Okay, so so when you do left plus right by 2, you're getting 3.5, but we're doing not left plus right by 2, but we're doing this, so which ignores the float before after 3. So your midpoint would be here. So now your midpoint is at index. Let's write indexes first. 1, 2, 3, 4, 3, 4, 5, 6, 7. So these are the indices and the midpoint is at 2, right? So now you compare your mid, which is 3 with 8. So 3 is less than 8. So when 3 is less than 8, we because mid is less than uh, the the target element, so we shift the left to mid plus 1. Now your left becomes 3. So mid was 2, right? So 2 plus 1 is 3. Your left becomes 3. Now your new left is 3 and your right is still at 7th index. So now you got your new left and right, and then you get your mid again. So mid would be left plus right by 2, which is 10 by 2, which will be 5. So this is your midpoint now again, new midpoint. Since you got your midpoint, you compare that with the target. So you're comparing 6 and 8. So 6 is less than 8. So now you again uh, increment your left to mid plus 1. So now your left would be 6. So now we got new left and right as left would be 6, right would be 7, and then the mid value would be 7. So now 7 is again less than your target, which is x. So because 7 is less than 8, we again increment your left. So left would be again mid plus 1, which would be 6 plus 1. So your left is at 7. So now your left is at 7 and right is at 7. So this is where your condition, you keep on doing that until your left is not less than right. So you're basically moving the left and right until left reaches right or right reaches left. So we've seen the condition where the mid is less than the target, and then we're moving left by left to mid plus 1, right? So I'll tell you what to do when you have mid greater than uh, the target. So that's when you do right. You're basically changing your right to mid instead of doing left to mid plus 1. You're changing your right, so you're shrinking the window by changing right and not changing the left. So because in this example we reached left and right now are equal. So now you come out of the while loop and then you return your left. So if you return your left, it'll basically mean you're returning 8. So which is this one. So this is the one that we have as target. So this is the point where you also return it. So that's how your binary search works. So yes, before jumping into the next example, let's look at another uh, example. Okay, now we until now we have seen the how do you do a binary search technique, right? Like to search an element inside an array, you've seen how do we do a binary search on it, which will drastically reduce the time that's needed to search for that particular element. Um, but the question here is, it's not a true binary search because they're asking for a window that is closer to x, which has the length equal to k. So the output that we're supposed to return here is a window that has the length of k, and it also has to be, the window has to be closer to x than any other window that is possible in that particular array. So let's look at an example that I have taken. So this is the array that I have taken. So x that I'll be considering here is 4, and the length, the window size that I need to, the window that I need to return should have the length 4. So the element that I'm looking for is 4, and if you plot that on a number line, so let's say this is 1, 2, 3, 4, 5, 6, and 7, 8, and 9, right? So in a typical binary search, what you do is you search for the, you basically take left and right and then compare it with, and then calculate mid by doing this. And then you compare the mid with the target element, which is 4 here in this case. But we're not looking for, we're not looking to see if that element exists in that window in the array or not. And we're not even looking to return the index of the needed element. So if they had asked us for to return the index of the element, we would just return 3 by doing the binary search. But that is not what they're asking here. So by looking at this array, if you have to choose a window which is closer to 4, so this is the element that I've, the target element, right? So if you just look at the number line, you can, but through common sense, you can just say that, okay, maybe this is the uh, valid window that we need to return, or this is the valid window, or this could be the valid window, or this could be the valid window, which will have the elements. First, let's take these. So 3, 4, 5, 6. Or maybe let's start from 2, 3, 4, 5. So because it has 4, I'm just doing this through common sense and not, it's not a logic or anything. By just looking at which window to return, you can just say these, yeah, 2, 3, 4, 5, and 3, 4, 5, 6, and 4, 5, 6, 7, or 1, 2, 3, 4. Okay, so these are the possible answers that, so one of these is our possible answers for our question. So if we want to know which is the answer here, we can just, so for example, in this particular window, the distance between 1 and 4 is 3, and the distance between 4 and 2 is 2, and the distance between 4 and 3 is 1. So what it means is we have one element which is at a distance of 3 from 4, one element at distance of 2 from 4, and 1. So the final distance would be 3 plus 2 plus 1, which is 6. Now let's look at 2, 3, 4, 5. So the distance of 2 from 4 is 2. Distance of 4 and 3 is 1. Distance of 4 and 5 is 1. Which again fundamentally means that we have an element which is at a distance of 2, and we have an element which is at a distance of 1, and we have an element of distance at 1 again. So now your total would be 3 and 4. So 4 is better than, so this is the kind of window that we need, and we would generally avoid, this is not a better window. So compared to this and this is a better one. So again, if you look at this, so okay, 4 is the needed element, right? So distance between 3 and 4 is 1. Distance between 4 and 5 is 1. Distance between 4 and 6 is 2. So we again got a total distance of 4. This is okay. So these two are typically better than the one window that we've seen before. So if you consider the last window, so 4 is the needed element, right? So distance between 4 and 5 is 1. Distance between 4 and 6 is 2. Distance between 4 and 7 is 3. So again, we have an window size, which is window which is not really a good one. So these two are the windows that we are not a big fan of. So 2, 3, 4, 5, and 3, 4, 5, 6 are the only windows we have an answer between these two. Now we have to see whether, how do we compare these two elements, how these two windows. We check the we don't really compare the number by itself, but we will compare the distances. So here we have the distance of 4 minus 2 equal to 2, and we have the distance of 4 minus 2 equal to 2. So how do you know which window to return? And because both the windows have a distance of, uh, so they're basically both good valid windows, but we decide to return the first window that because it has less, because it has the, I think they've asked us to return, and if so, if an integer a is closer to x than an integer b, if this particular thing is valid. So if both the numbers are at the same distance from the target element, we have to return the one that is smaller. So in this case, 2, 3, 4, 5 would be our valid window. So this is the one that we have to return. Okay. Now let's take the example that is given in the problem. I'll take the example 2, which is better than the example 1 because it has more number of elements and we can have some liberty. Okay. So I've taken the example that is given in the problem. So again, the idea is for you to find the window which has a length of 4, which it has to be closer to -1, which is the target. So x here is -1 and k is 4. So your window basically should have a the length equal to 4. So it could be window starting from 0 and ending at 3, or it could be the window starting from 1 ending at 4, and it could be the window starting from 2 and ending at 5. And you don't need to really go into your starting point of the index cannot start at 3 here, because uh, then you won't really return a window which has exactly the length equal to k. So if you start your window from 3, index 3, you can only go till 5, fifth index, right? So beyond fifth, there is no other element. So this window, even if you see that this is closer, then this window will not be really valid. So it's better you skip the other operations beyond this number. So you get this number by subtracting the length minus k. So the length here is 6. 6 minus 4 is 2. So you basically stop your assuming, okay, your starting index is only among these three indices. So 0, 1, 2, 1, 2, just those are the start indices of your possible valid windows. If you draw the numbers that are given, 1, 2, 3, 4, and 5. So only these are the elements that are present in the array, right? So now we are plotting our x minus 1. So we now have to find a window which is closer to x. Okay, now what we will do is, okay, so in this particular question, we will take our left and right, as you've seen in binary search technique, but the right here should not be equal to length of your array minus 1. So technically, which means usually when in our binary search, we take our right index as the end index of the array, right? So this we can't do it here because even if your window starts from 5, there is no other elements for you to go forward. So this will be a invalid window. So the right will end at length of array minus k, which will be equal to 5 minus 2. Sorry, 5 minus 4. Uh, sorry, the length is 6. So the k is 4, and then your right would be 2. So this is our right and this is our left. So as you did in binary search as well, you have to basically find a midpoint by doing left plus right by 2, and then you get uh, 0 plus 2 by 2, which is 1. So now you you don't compare the mid value with the target value as you do in binary search, but we will do um, x minus the mid and x minus mid element. So this, so yeah. So you're basically uh, comparing the difference between x and the mid element and x minus mid plus kth element. For example, in this situation, we're comparing. So the mid that we've gotten here is 1, right? So the element at 1th index. So we are comparing x minus 1, which is minus 1 and minus 1, and we're comparing x plus k. Mid plus k, which mid is 1 and k is 4. So 1 plus 4 is 5. So minus 1 and minus 5. So now we are taking the absolute values and not uh, okay, so minus 2 and minus 6, right? So we're taking comparing the absolute value. So 2 and 6 we're comparing, and 2 is lesser than 6. So because 2 is lesser than 6, we change our right to mid. So earlier this was our right and this was our left. Now our right becomes this. Left is unchanged. So left is still at 0 and right is at 1. So now you again do mid. Your mid will now be 0 plus 1 by 2, and then you get 0. So now you compare the 0th element, again x minus the 0th element. X is minus 1 and the element at 0th element, 0th index is 1, and we compare mid plus k. So 0 plus 4 is 4. So we compare minus 4 minus 4. So minus 2 and minus 5. So now because we're comparing the absolute values 2 and 5. So 2 is lesser. So we again move our right to mid. So earlier our mid was this one, right? So now our left is at 0, right is at 0, mid is also at yeah, so mid was at 0 and left was at 0. Now your right has also moved to this one. So because now our left is no longer lesser than right. So this is when our while loop stops and it will come out of the while loop and we return the index left. But the returned index is only the starting point of the window. So we have to return the entire window, right? So we'll do left and left plus k. So this is where this is a valid answer, and the okay, left to left plus k is array of 0 to left plus. So that would become, the answer would be 1 1 2 3. So that is how we return the closest window for our closest window to our element x equal to minus 1, which has a window of 4. Okay, let's look at how the code would look like. So as I said, the left would start from 0 and the right would be length of array minus k. So you need to remember that left and right are not the indices of our valid window, but they are the possible starting indices of our valid windows. So, okay, now let's do, let's check the mid. Mid would be left plus right by 2, and we'll check the difference of x and the mid and x and mid plus kth element. So if x minus mid, so we have to take the absolute value. So if x minus mid, um, x minus, sorry, array of mid is greater than absolute value of x minus array of mid plus k. This is not bars, it's abs. If it is that way, then we will um, do left will be equal to mid plus 1, else right would be equal to mid. Okay, now we have to make sure that this whole logic will continue until left becomes right or right becomes left. Now we return. Let's try and print it first. Print of left. There is an expected. Okay. Okay. So then we are printing 0, which means this is the starting index. 0 is the index of the window that uh, we are returning. So 0, 1, 2, 3 are the indices that we need to return. So we'll return the window which has the starting index as left, and the ending index would be left plus k minus 1. But we only mentioned left plus k because it will, of course, only print till the 1 less than that. Okay, now it's accepted. Try and submit it. Okay, we have a index out of range error. Okay, let's try and hmm, have we done something wrong? Let's see and take out. Okay, we're getting the index out of range. Oh, yes, finally. I think when you're not including the parentheses, then it'll only, the mid will be calculated as left plus right by 2. So it'll do right by 2 and then it'll add it to left. I think. I'm not sure, but yes, uh, this is how you do the binary search. And this, I'm not really sure why this has been mentioned in the neat code sliding window section, but anyway, I think it is only because of course, we're sliding the window here. For example, we're considering this and then we're comparing it with the x element by comparing x minus, for example, if this is our mid, the element at 0th index, which is 1, 1 minus 3 and 5 minus 3 we're doing, and then whichever one is closer, that uh, depending on that, we are sliding the window. So I think this does come under proper sliding window. I'm not sure. You tell me. Yes, but this is more like a combination of binary search and sliding window approach. Anyway, so this is how you solve this question.